Welcome to the course on two-dimensional signal processing principles and practices. As we are doing the 2D FIR filter design, we had seen one method in the previous lecture. So we'll see the rest of the methods, frequency sampling method and the frequency transformation methods in this lecture. So 1D frequency sampling method, that is the frequency sampling filter design. So if we take an FIR filter structure in which this y of n, the equation of the 1D FIR filter is equal to h of 0 into x of n plus h1 x of n minus 1, and it continues up to h of n minus 1 x of n minus 1. So we had seen that in the 1D filter design, the structure and its equation. So this equation, the order n can be defined from this number of delays it uses and the coefficient also. So the number of coefficients have been given in this diagram, whereas h of 0 is the first, second, third, and all these coefficients are h of n minus 1. So the x of n, the input signal is delayed and then further delayed one time, and each delay is multiplied with a coefficient and added it. Or the structure what we had seen is you have the x of n and then multiply by the first coefficient and then delay it, multiply by the second coefficient and add it over here, and then that addition can be added to the next delay and then multiplied by the coefficient and add it. So that's the direct form 2 we had seen. That way also it is, or you can use only one adder or to sum up all the delayed sequences of xn, which was multiplied with the coefficients at the appropriate instances. So this y of n is giving the output of the filter structure. The order depends on the one which we want to design, also the specifications used for the design. So this is simple 1D FIR filter structure and its equation. So this is an n tap. We generally call it as depends on the taps used. That's the coefficients. That's the coefficient of this filter, and it's an n tap. We call it as taps. So n tap non-recursive FIR filter, it doesn't have any recursive structure in it. So if we extend that 1D filter structure to get the same one using the frequency sampling method, in which that x of n is the input and y of n is output, and in between the structure is different compared to the one which we had seen, how these coefficients matter, and the delay, simple delays of the structure is now made in the frequency sampling structure, where it's a combination of comb filter and a resonator. So comb filter structure is this, which is common to all the resonators which were specified here. What was the complex resonator? What does it do actually in the filter design? So we would see them like the comb filter, which has the equation of this is supposing y1 of n. Let us take y1 of n to x of n is going to be y1 of z by x of z, which is equal to 1 minus z per minus n. So this has a delay, a simple structure x of n minus x of n minus n. So that's the y1 n equal to x of n minus x of n minus n. So this is the comb filter equation, difference equation. So this is called comb filter because it has n number of, if we take the structure of it, it will have n number of zeros on the unit circle in the z plane. This is the z plane. So this is real of z and imaginary of z. So this will have the number of holes, number of zeros can be 4 or 8, depends on that. Suppose it is 8, it will have the zeros on the unit circle. So it depends on n what we have. So we can substitute here x of n and x of n minus 8, and so we get to the frequency response of this h of e power j omega. The magnitude would be, so this fashion, which is where this omega is varying. So this would have 0 to pi. Here the number of combs will be in the structure of this h of e power j omega, in which this is 0 and the next 0 would be here, this point and this point and this point, and equally spaced zeros on the unit circle. So this is the pole zero diagram and the frequency response, especially the magnitude response of it. So if you have the frequency response in which the phase response, so the phase is linear over here, it would have the linear phase in between, and so this will have the 2 magnitude. If you just substitute this z equal to e power j omega, and we will get the frequency response as this with the magnitude 2. The thing is here where this response is going to be 0 and here it will be peak, and these frequencies are passed and this one will be attenuated and completely removed. This is wherever the zeros are placed, that will be completely removed. So this is the comb filter structure, and with this comb filter structure there is a resonator appended or the cascaded with it. So in this case, suppose the first one, if we take h of 0 z 1 by 1 minus e per j 2 pi k by n, where k is 0, so that is going to be 1 by 1 minus e power minus 1. So this is for the k equal to 0. So with this, if you put k equal to 0, that would result in a pole at this point. So 1 minus e power minus 1. So this cancels this 0, and then having this DC to be passed over here. That is the maximum response over here, that would contribute to the maximum response, k equal to 0. So that this resonator would pass only the DC. So for supposing taking this say second resonator where k equal to 1, so then that resonator is centered at the k equal to 1, which is the fundamental here. This is the fundamental. So if this is k equal to 0 and k equal to 1 and so on, so the number of resonators we can fix for which we need the response or the frequencies should be passed. So for example, we want to pass DC and fundamental. So we can make these two resonators on and the rest of them to be removed from the structure. So that means the structure can go up to k equal to n minus 1. So we can choose the resonators, which resonator we just only give the peak at that particular k value or the frequency what we choose. So this can be fixed over here or this can be fixed over here, fundamental, second, third and other harmonics, which we are interested to take out from this input signal. So and if we keep increasing the resonator, so the width of this each sync pulse can be added together so that it can form a band pass filter. So we will see this in through this example. So right now we can have the filter structure which can be a low pass or which can be a band pass, and depends on the frequencies needs to be passed. If it is set of frequencies from 0 to second harmonic to be passed for a low pass filter, and then about second harmonic to be removed, then we can have this 1, 0, 1, 2, 3 resonators here in cascade with the comb filter, and there is a coefficient which is h of 0, h of 1, h of 2, and n is the number of samples we use it here in this in the filter structure. So added together, it will form a low pass filter with omega and h of e power j omega. Magnitude would be these three, k equal to 0, 1, 2 are passed and remaining are 0. So how do we get this? Here is this is the response of the central response of the DC resonator and the fundamental second harmonic. So this is the cascaded structure, and the addition of the resonators would result in the frequency response like this. So individually if we take, this would give the frequency response. So individually we could say that this would give a frequency response over here, and this would have the frequency response of this, and the second one will have the frequency response of this. So individual bins will have a peak response at a particular frequency. Adding up together with the number of resonators required would result in a low pass filter, and the resonators which are switched off or made it 0 would give the attenuation band or the stop band here. So this can be similarly chosen for k equal to 0, 1, 2 and then you stop for k equal to 3 and 4 and 5. Suppose I want to pass it again, that 6 and 7 I want to have the frequencies to be passed through this filter, then we can switch off this k 3, 4, 5 and 6, 7, 8 can be again made it on like that. Okay, so this can be continued with this is one pass band and this is another pass band. We can have the band of frequencies which is to be passed for which k is existing, and the other resonators can be switched off from the or removed from the structure. So this is how the sampling filter works, and what is the meaning of this here each resonator. So x of n, which is, and y of n, input and the output, what is the relation between these two? So the resonator has this one comb filter, and here we have the 1 by 1 minus e power j 2 pi k by n and z power minus 1. So this is the feedback structure of the resonator. So this portion contribute to the k, depends on k equal to 0, 1, 2, 3, it would give the peak response. So this is contributing to the zeros on the unit circle. So if we just want to have this as I explained here, this is 0 and 1, 0, 1 and then 2. So it would have individual responses like this, and the k equal to 1 response will be like this, and k equal to 3 response would be like this. And if we want to change the k equal, then 3, 4, 5, as I said 0, and 6, 7, 8, I would like to have again the band of frequencies to be passed. So this is 6, 5 and 6, or 6, 7, any of these values we can have, 3, 4, 5, and we'll call this as 6, 6 and 7, and this is 8. Okay. So in that case, the addition of these individual bins would be the response of the, so you'll have the response, it will have a ripple as like this, and it will have a ripple, and the addition of all these bins would result in a band of filters. So this depends on the resonator what we choose. So it's a sampled version here. This is called the frequency sampling filter. So because the k in which this k's, different k's can be chosen for it. So the summation of all these resonators plus a comb filter, the comb filter and h of k, and h of k by n, if you have this is one resonator with the comb filter structure. So 1 minus e power j 2 pi k n z power a minus n. So what is this h of k and what is the maximum value it can give? So substituting z equal to e power j omega in this equation. So where here e power j omega n, this is going to be again 1 minus j 2 pi k by n into e power minus j omega, and if we combine these two, we get h of k by this. So what is the magnitude and phase of it? So we can always have this 1 minus e power minus j omega n by 2 and simplify it. We can get this, also can be simplified to get the sign by sign or a sinc function for this one resonator, and this is the phase portion of it, phase terms, and this is the magnitude term or amplitude terms. So to get the amplitude term alone, this would contribute only in the phase term. This is a simplification. This equation is a simplification of this by having the n by 2 and so on. So here we can also simplify it using the sine and cos, writing it like cos of omega 2 pi k by n minus j sine 2 pi k by n. So we can get these terms get cancelled and we have sine by sine terms. So this is the simplification of the frequency sampling filter 1D, and amplitude of it, we take this term alone and find out omega equal to 2 pi k by n. When we substitute this, what is the so differentiate it should not result in 0 by 0. So differentiate it and get the expression as this, when you substitute omega equal to 2 pi k by n, that would give the n minus 1 per k. So this would give you a maximum amplitude of n into minus 1 per k. So this one which we have the amplitude alone. Okay, if we take the phase of this particular equation, so this is the first phase term which we had h of k. So this phase term will be resulting into minus 1 per k, when we have this magnitude or the omega, which is to be substituted as 2 pi k by n. So this case phase and magnitude term, so the magnitude response, the response of it, what is the maximum response it can have? So h of k, its magnitude and whatever the value, and then n into minus 1 power 2k. So this is coming from the amplitude response and this is from the phase response. So here we get minus 1 power 2k. So the h of k magnitude into n is the maximum response. We can get it at omega equal to 2 pi k by n. So that needs to be divided by n. That's how we get at the structure, every structure what we have, the resonator structure in which here we are dividing it by n. So the maximum response will be n into something. So we divide it by n so that get the maximum value here 1. So from that one resonator structure, can we combine this to have a summation or the multiple resonator structure. So the frequency response of the design filter, which is having this 1 minus e power minus j omega n, this is coming from the comb filter, where z is substituted as j omega, e power j omega here, and the k is varying from 0 to n minus 1 h k by n. You can notice this n, why it is has been put over here in the structure, 1 minus j 2 pi k e power minus j omega. So here, so this is the equation which is used for the frequency sampling filter for the design of FSF 1D. And this k, if we choose, that would result in number of resonators actually. So number of resonators can be added, that is in the structure, depends on the peak response what we want for the filter design, and what the frequencies to be passed, what are the frequencies needs to be there in the output, and what are the frequencies to be attenuated. So that depends on that, k would be chosen, and summing it up, adding all the resonators together and multiply it with the comb filter 1, it will give the frequency response. So this is 1D. Extending this to 2D, like the same concept of this can be extended to this 2D, in which the 2D frequency sampling method, in which the desired response HD of omega 1 comma omega 2, that is going to be, suppose it is a low pass filter, it is going to be 1 for certain range of omega 1 and omega 2, and 0 for the other cases. So this can be again like circularly symmetric, and the case of separable window, separable response. So the HD of omega 1 omega 2 can be of any of these two. So as we have seen in the previous lecture, so what are the separable response and the circularly symmetric response. So HD of 1, for ideally taking, this is going to be 1 for some certain region, and then the rest of them it would be 0. It can be a circularly symmetric, or it can be a separable response. So for taking this as a HD, that is the desired one. So if we sample that desired one at for omega, if we e power minus j omega 1 n1 by 2, e power minus j omega 2 n1 n2 by 2. So this minus 1 and minus 1 comes into picture because this is taken as odd, n1 and n2 are odd. So otherwise it is simply n1 by 2 and n2 by 2 if it is even. So and omega 1 is 2 pi k by n. In the case of 1D, this is also extended to 2D, 2 pi k 2 by n2 or 2 pi k1 by n1. So this h of k1 comma k2, just HD multiplied by this thing like here would result in h of k. This is the sampled version. What we say, this k1 is varying from 0 to n1 minus 2 and k2 is varying from 0 to n2 minus 1. So these samples, actually equally sampled points we get in the 2D, or as we have seen in the 1D. So we can have this number of like resonators where are all we are placing. So this is also the resonator in each direction, W1 and W2, you will have the resonators. So that it's a sampled version. We just want to show that this is going to be a sample points of h of k1 comma k2. So this h of k1 comma k2, if we take the inverse transform of it, that is inverse Fourier transform, that is IDFT of h of k1 comma k2 results in h of n1 comma n2. So actually speaking, what is the h k1 comma k2 is an approximation of this desired one. So what we design here is not exactly the ideal response HD, which is the desired, but we'll get the approximate or the actual responses. This h of omega 1 omega 2, this is called, in case of the desired one sampled at certain points is the h of k1 comma k2. With this, if we design h of n1 comma n2, the inverse one, IDFT of h of k1 comma k2, and moreover in the FIR filters, we learned that how the linear phase structure helps in it. So linear phase structure in which the structure what we had in the 1D also and the 2D also, it reduces the number of independent terms. So it is easy for the estimation. So the more the symmetry, more we can get the estimation reduced. That is the case of less number of independent terms. So h of n1 comma n2 is equal to h of n1 plus n1 minus 1 by 2 and n2 minus 1 by 2. So if we make these coefficients equal, then we can have the zero phase filter. We had seen with one example of window method or 1D. So this would be, and we had also the 2-fold symmetry, 4-fold symmetry and 8-fold symmetry. Likewise, if we have these coefficients equal, then the linear phase can be obtained, linear phase of the filter can be obtained. So taking this h of omega 1 omega 2 and the relation between h of k1 comma k2. h of k1 comma k2 is the desired one sampled, and if we take the inverse of h of k1 comma k2, that you get h1 h2. So from that Fourier transform we can have this h of omega 1 comma omega 2. So how these two, so this is nothing but h of omega 1 comma omega 2 is going to be the sample. So here what we said, h of k1 k2 equal to hd into minus of j. So here hk into this plus would give you that h of omega 1 omega 2. So it's an actual filter which is designed. So we can recognize this now. This portion is nothing but the comb filters in both the directions. So 1 minus z power minus n1, and this is z power minus n2. So this is the first one what we had in the 1D. So this similar equation that is extended to the 2D also. And this summation we had seen for different resonators. So this is one resonator part, e power j 2 pi k1 n1 e power minus j omega 1. This is z power minus 1. And this is also z power minus 1 here. Okay, so this is with the omega 1 and omega 2. And this portion is the e theta k, that is e power j 2 pi k n1 by n k1 by n1 e2 pi k2 by n2. So this is another theta k. So this is for k1 and this is for k2. These two are contributing the poles, 2 poles in the z plane of the 2D. So here the one which is due to the resonator, this is another resonator, and h of k1 comma k2, which is a constant minus 1 power k, we got it, and that into n for the maximum. So we divided by n, that is n1 into n2 here. So that compensation is done instead of having it by n1 n2. So it's outside. So this portion, this total portion is going to be the h of omega 1 h of omega 1 omega 2, and where it is multiplied to get the omega 1 omega 2 here. This is the desired response here. So desired response, from desired response is always ideal, and from that we get h of omega 1 omega 2. The equation can be interpreted and compared with the 1D case to get this frequency response. So this is the frequency response of the designed filter h of omega 1 omega 2 here. So using this method, we will show that one or two examples of the filter what is designed. So here is a 15 point here, 15 into 15 in 2D. You can see this 15 by 15 window, that is W1 and W2, and this is the low pass filter which is to be designed with 0.4 pi as the up to 0.45 should be the pass band, and this from 0.5 to rest of this pi should be the stop band. So in between 0.4 to 0.5 is the transition band. So if that is the case, this is the sampling grid of 15 by 15 point. So the filter which is designed using this frequency sampling one. So we need to add the low pass filters for here k equal to this up to here you can have the 1 2 3 if it is, and then these resonators should be avoided, and only these resonators should be there in the structure. So we need to fix k, what is the bin index corresponds to fundamental, second and third harmonic. Accordingly this omega can be translated into that. So we can have these samples, these resonators to be added in the summation, and the resonators of the rest of the thing should be removed from that. So the filter structure which is designed for it, 15 by 15 point low pass filter. In this case, like you can have the ripple, the passband ripple. You can see this is not a very fine ripple which we have, and you can see the ripples. This for the case of circularly symmetric, you can see the ripples all over here, the passband as well as the stop band, in which the contour plot is also shown over here, the corresponding contour plot. The filter which is having the more ripple in the passband and the stop band in this case. So the frequency sampling filter, obviously you have the frequency response, that is peak response for 1 2 3. So if we add them together, okay, so then you can see that this is how this has been done, like in the 2D case. So this 4 k values has to be added to get this passband one, and these are the rest of them which are the stop band frequency which could be visualized in this fashion. So the number 15.15 has been used in this case. We can even say that the grid change and the resonator change can be applied, and depends on that what is the passband frequency, 0.4 to 0.5. The transition band can be varied further also, or we can remove the resonators which are not required, or we can adjust this passband to either widen it or shrink it. We can do that as well. So but the one which is used here is that we have the 15.15 point grain. In that band pass also we have, suppose 0.3 to 0.4 pi is the pass band, which is the one here, and the 0.7 to 0.8 also here we have the another band of frequencies. So in between this would be passed and this would be removed and this would be removed. So here is the 0.4 to 0.7 is the band of frequencies which are passed. So the rest of them are here between here. This is the transition band and this is the transition band, another transition band in which between 0.4 to 0.7. So this is a band of frequencies which are passed. So you can see the ripple over in this portion here. So this is also circularly symmetric. This is the example of this band pass filter and its corresponding one. So here is this band is passed. So here we have the 0.7 to 0.8 and this is the one which is having 0.3 to 0.4. In between we have the pass band here. So this is a contour plot just to visualize the top view of it. So the band of frequencies, for this band the Ks are retained and the rest of them the Ks are reduced. So so if you compare it with the window method, so what we had designed already, the window method gives you the ripples less, depends on the window you choose. So if you choose the better window, then the stop band ripple and pass band ripple will be more or less equal. But whereas in this case, that this pass band ripple is more, if you see that in the picture, the pass band ripple is more in this case. So frequency, it's not optimal method with the frequency sampling filter, and the region of support is often longer. In the sense, for the same specification, if you use the window method and the frequency sampling filter method, the number of resonators required in this case are h of n1, n2, the number region of support, the filter coefficients what is required will be larger compared to the window method. In that, this is lack of control over the frequency domain parameters, because k is exactly, we have to choose what are the resonators required in the case. So in the practice, this is used, FSF is used because it has less number of computations. Only the summation of that, the computational complexity is simple, and the conceptually, if you say what frequencies are required around which the resonators can be retained. So in that way, this is simple method, but it's not an optimal method if we compare it to the window method. Also, the coefficients required for this case is more compared to the rest window method for the same specifications. So from that, we can also have the second, the method is the frequency transformation method. So wherein what we do is, in the 1D case, we design a filter that is in the analog specification, whatever, and within the analog itself, we can use the transformation, the one frequency to another. For example, low pass is designed for a particular frequency, which is having the frequency omega p as a cutoff frequency. We designed it, and because it's in analog domain, you have the Laplace variable s. So the filter is designed with the Laplace variable in the analog domain. And this S is whatever the transfer function we get for the 1D filter, analog filter, want to change the cutoff frequency to another one. So then this case is that you just use that frequency transformation. So using this omega p dash is the next frequency or the new frequency for which they need the transfer function of the 1D. So that omega p, using this transformation, this S is replaced with omega p by omega p dash S. So this transformation is used on every S, so that the designed filter is transformed to omega p dash as a cutoff frequency. This is for the case of low pass. Similarly, if you want a high pass filter, so the low pass filter which is designed omega p and S is replaced with omega p dash by S. So the passband frequency is different for the case of high pass filter. Then the frequency transformation used is this. These are standard frequency transformations. And suppose you have designed this low pass filter and then we want to design the filter, band pass filter from it. So the frequency transformation which is used is that omega u and omega L are the lower and upper cutoff frequencies of the pass band or the band pass filter, what is required. So lower cutoff and upper cutoff is the band of frequencies which are passed. So likewise in the analog filters, we have the different kind of transformations available to get the design done. So from one to another, that is from low pass, high pass, band pass, and then band stop filter. Similarly, for if we have the pass band frequency is omega p, and multiply that with s into omega u minus omega l by s square plus omega u omega l. These are lower and upper cutoff frequencies of the filter to be designed. So then the low pass filter, which is designed already, can be simply used for this, the transformation can be used in that, and get the band pass, band stop, high pass, and low pass filters. So this is in the analog domain, where the prototype is given as low pass with which omega p is there. Now the same transformation is applicable in digital also. So the digital transformation, suppose you have this Z dash, you got the low pass filter, the or the difference equation, or the z domain transfer function of the low pass filter. In that case, every z minus 1 is replaced with this z minus 1 minus a by 1 minus a. This is a standard way of doing the transformation from one frequency to another. So the omega p dash is the next bandage frequency of the new filter. So in which that a is omega p minus omega p dash by 2 and omega p plus omega p dash by 2. So this a is now changed here. So every z dash in the transfer function is replaced with this and get the new transfer function using this transform. So similarly, for the high pass, you can have cos omega p plus omega p dash, omega p minus omega p dash. So where is a replaced? For band pass, similarly, every z inverse is replaced with this big expression where a1 and a2 are corresponding to the lower and upper cutoff frequencies, where k is involved in this, k is given here. So band stop filters, these are the standard tables available for the frequency transformation. So this concept of designing the filter in one frequency and then transforming it to the other frequency as the same filter as low pass are different filter designs, high pass, band pass, and band stop filters also possible in that case. So likewise in 2D, so we can design the filter in case of 1D, or use the 1D filter and then transform it to the 2D. So that is what the method is called, the frequency transformation. So how do we do that? What is the methodology involved in it? We'll see that one method. And basic idea of this 2D frequency transformation method is, we have h of omega, that is 1D frequency response is known. That means with the given specification, we can design this h of omega, and that omega we replace with a transformation function, or which is g of omega 1 omega 2. It's a function of omega 1 omega 2. The g is function of omega 1 omega 2. Omega 1 omega 2 are the variables of this frequency response of the 2D filter to be designed. So if you just replace this omega, what is in the 1D, with the transformation function, so that it becomes a 2D. So this is the basic idea, and h of omega is the 1D digital filter here. The first one which I had shown, the first table was the analog filter, but the second table was the digital filter in 1D. So similarly, we are talking about the digital filters here. So the 1D digital filter, h of n to be obtained, like in the 1D window method we had got. So and find its frequency response h of omega, and h of omega 1 omega 2 is the 2D which is obtained from h of omega, and using this transformation. So what are the, so if we just look at this of omega and h of omega in this diagram, this is the band pass filter, suppose. So this band pass filter which has this frequency omega naught, omega 1, and this is omega 2. So this is a transition band, and these are the pass band, and here is again the transition band. So how this is transformed to 2D? So that's what the picture which is shown over here, in which h of omega 1 omega 2 is obtained by substituting this h of omega, where omega equal to g of omega. So the transformation function, we will see what is the function which is practically used, at least one function, g of omega 1 omega 2 for this transformation. So omega naught, you can see that this is omega naught, which is transferred here to that and are transformed in this 2D. Similarly, omega 1 dash here, and the stop band here, the transition which is allowed in this is omega 2 dash. So this one. Okay, so g of omega 1 omega 2 equal to omega 2 dash. So we can get in the g of omega 1 omega 2 are the transformation function equated to omega 2, omega 1 and omega, whatever it is, we will get this type of h of omega 1, omega 2. So this represents the contour. Each one is when it is equal to omega, it is representing a contour. We will see what are the contours in this for the particular g of omega 1, omega 2. So this is the basic idea of transformation factor. So there are two issues can be. One is zero phase filter, or the linear phase needs to be obtained. We should have the h of n1 comma n2. What we get it as an inverse transform from this should have a zero phase. That means the coefficient should be symmetric, at least two-fold symmetric, and then the transformation function should exist. So that's the from here to here to the transformation, this transformation function should exist. So that's the two issues which can be faced in the what transformation function we'll use. That's the issue here. So the case of 1D 0 first h of n1, h of n with length 2n plus 1. Suppose n is this and 2n plus 1, we have the length n equal to 10, then it will be 21. So n equal to 5, it should be 11. So likewise this 1D FIR filter h of n can be. So the frequency response of this can be from minus n to plus n, h of n e power minus j omega n. This is known from the DTFT equation. And then if the symmetricity applied, h of n equal to h of minus n for a linear phase filters, then it is going to be this function can be related as for 0 only separate it, and the rest of them 1 to n will be 2 h of n cos omega n. So this is also can be simplified as n equal to 0 to n. So all these coefficients together, e of n cos omega n. This can be further simplified, but we can also say that for this one can be cos omega in order to get the transformation function. So cos omega power n. So this cos omega n, which is here, can be represented as some linear combination of 1 plus cos omega plus some into cos omega square cos omega power n. So this can be written in terms of this. So there is a proof. We are not doing the proof, but we are just changing that to this b of n is cos of omega power n. So these things, b of n is not exactly the h of n. So this has the coefficients here, the linear combination of cos omega power n. So this we are just replacing cos omega with b of n cos omega power n. So this is going to be the h of omega 1D frequency response. So from this 1D frequency response, we will see the 2D one. So for the 2D frequency response, what we do, h of omega, what we had obtained in the previous step, where omega equal to sub g of omega 1 comma omega 2. So in that case, that what is the transformation function used is cos omega equal to t of omega 1 comma omega 2. T, it's a function again. T is a function. So if we substitute this omega equal to, in this case, cos omega 1, cos omega what, cos omega power n is replaced, cos omega is replaced with t omega 1 comma omega 2. This is a transformation function, and which is represented as, which is also in the frequency domain. And this frequency domain, if we take the inverse Fourier of it, that is equal to, that will have a sequence t of n1 comma n2 e power minus j omega 1 n1 e power minus j omega 2 n2, where we get the inverse of this. This can be done only if we know this transform or the transformation function. So from this, if we will have some coefficients, we can adjust these coefficients by substituting this cos and sine, and that would, those coefficients are called as c n1 comma n2. So we have seen this one can be written in terms of cosine terms in the previous examples, the lectures as well, c of n1 comma n2. So here, if we once we obtain this, this has a region of support. The standard function which is used here is the one for the transformation function is minus 1 by 2 cos omega 1 and 1 by 4 here. So this can be simplified further to have t of omega 1 comma omega 2. So this is a practically used transformation function for the design. Either it is a band pass or band stop filter or the low pass filter. We use this omega, we choose this omega and then get this transformation function. So this is called, this Macmillan is used to this transformation function. So it is called in his name. And now what is the 1D type which we have? So 1D in which delta p, delta s, omega p, omega s are defined. That is passband ripple, stop band ripple, passband frequency and stop band frequency. And the desired frequency response is always 1 in the case of low pass filter with up to the passband, and rest of them it is 0. So using this using this we'll design the filter, that is one. So t of n1 comma n2, which is the region of support of the transformation function, suppose 2m1n plus 1 and 2m2 plus 1. So, the length we had already seen that 1D filter is 2n plus 1. Then what is the 2D filter region of support will be 2m1n plus 1, 2m2n plus 1 here. So, for n equal to 10, m1, m2 are supposing 1 here. So, the region of support of the transformation function is that 1, then you will get T of n1 comma n2 is 3 by 3 and this is 21 because of n 2n plus 1, and the h of n1 comma n2 what we get is here, this is 21 cross 21 coefficients. So, for n equal to n, the length of the 1D filter. So, this decides this and the transformation function as well deciding the coefficient length. So, for example, that what we had taken T of omega 1 omega 2 has the region of support is this. So, if we take the T of omega 1 omega 2 and plot it, take the inverse Fourier transform and plot it this, and its coefficient C of n1 comma n2, if we take it in the cos and cos linear function of cos, then you can see the independent terms which are to be available here. So, these are the terms which are only for the C of n1 comma n2. So, this is obtained, C is obtained from T only. So, with the combination of cosine, linear combination of cosine function. So, this is the filter coefficient and or T of n1 comma n2. Using this T and H, we can have the H of n1 comma n2. So, the transformation function, that is how do we obtain that? So, cos of omega we equate it to T of omega 1 omega 2, that is the big expression, in which if you substitute omega equal to 0, this result in a one contour omega equal to 0.1, 0.2, 0.3 and 0.4 pi and 0.8 and 1 pi. So, this contour you can see this is used for circularly symmetric filter designs. So, transformation function used for that. So, whereas cos omega is T of omega 1 comma omega 2. So, you can see the contour, we can choose the contour which one want to be. So, suppose I want the band pass filter to be having 0.3 and having this up to 0.6, we can have this whole contour. I have the low pass filter which has the passband frequency of 0.3 pi and the transition is 0.3 to 0.4 and rest of them should be 0. So, we can choose that transformation function to be used in this case. So, supposing this is omega, h of omega which has 21 point and it's 2D, you can see the 2D which is after the transformation, the filter structure give this. So, in the what is the to consolidate the method what we discussed here, this first method, choose this T of n1 comma n2, that is from the transformation function, and get the specifications what is given into the h of omega 1 omega 2 to h of omega, translate it and then design this h of n using the window method or the Park-Maxwellian method or the case any of the 1D filter design, and use this h of n and the T of n transformation function, the T of n1 comma n2, the region of support what we get, from that we can get the h of n1 comma n2. So, just to give an example here, suppose delta P and delta S are 0.05 and 0.025, this is ripples in passband and stopband, and passband frequency of 0.45 and the stopband frequency of 0.55. So, this is the low pass filter specification. For this, how do we design this filter? So, take the transformation function and then we have the equivalent would be, so choose the contour cos omega equal to this, where omega you substitute as 0.45 and substitute as 0.55, you will get these two equations here. So, that is corresponding to the contour. So, delta P, from that we have in the step 2 transfer the specifications to 1D. Delta P dash and delta S dash stop band and pass band ripples here are taken as such, and omega P and omega S dash, these are the 2D ones which we had converting it to 1D transform. So, 0.45, and if you look at 0.5, we can have this 0.5 also. 0.5 is exactly the little change in the contour. So, we can look at the contour and fix this as near to the 0.5 which is 0.486. It's not exactly the giving the contour properly for the circularly symmetric one. So that's why it is taken as 0.486. You can adjust this in the design using the transformation function contour. So instead the cos of omega equal to T of omega 1 omega 2, that omega can be chosen this and see the contour here. So there is in this design procedure adjustments. This would fit in exactly in the contour, but this one 0.5 is not. So we can slightly adjust that to get it exact contour. Then the Park-Maxillin method obtained the 1D h of n. That is, h of n should be equal to h of minus n, because this method we will discuss maybe in the next lecture how do we do that Park-Maxillin algorithm, and determine this h of n1 comma n2 using this hn and t of n1 comma n2 what we had got. So likewise this method is giving 31 cross 31 point low pass filter, and band pass filter is designed in the same way with 0.3, 0.4 and 0.6 and 0.7. So 0.4 to 0.6 is the band of frequencies to be passed, and rest of them the below which should be below 0.3 should be cut off, and below 0.7 after 0.7 should be cut off. So the transition width is 0.6 to 0.7, and similarly here transition width is 0.3 to 0.4. So with this, the contour plot and the plot is given, but it is resulting 41 cross 42 band pass filter using this frequency transformation. So we had looked at the two different methods of FIR filter designed in this lecture. One is this frequency sampling filter, another one is a frequency transformation method. So frequency sampling filter design, in which 1D case we have to choose the k values for the resonators for which we need the band of frequencies. There is the pass band and the stop band. So the k of stop band should be neglected and the k of pass band should be added, or the resonator should be kept to have the band of frequencies to be passed. So this should be done in two directions, k1 and k2, as we have seen in the frequency sampling filter. So there is a ripple involved in this pass band more compared to the window method, and the number of region of support is also more in this case of frequency sampling filter, but it is computationally efficient and simple and easy to implement filter. So we prefer it in practice for the frequency sampling filter. In the frequency transformation, we use a transformation, design 1D filter and use the transformation to have it in the 2D. So 1D filter specifications should be taken in this case, for which if the design is given in the 2D where filter specifications are given, we transfer into 1D and then choose the transformation function corresponding to the cutoff and cutoff frequencies or band of frequencies to be passed. So use that and get the region of support using the inverse Fourier transform and the coefficient as obtained from the 1D filter design, and use this to get the h of n1 comma n2 as we discussed in the method of Park-Maxillin, which is the transformation method used. So we'll see the design method too, and how do we do this in the MATLAB code, the implementation of this frequency sampling filter and the frequency transformation method of designing the filter in the next lecture. Thank you.